Have you ever wondered where the absolute bedrock of modern artificial intelligence actually comes from? You know, the kind of tech powering everything from your voice assistant to cutting-edge medical diagnostics? You would probably think it was discovered yesterday in some sleek glass-walled tech campus. But it wasn't. Let's dive right into this explainer. What we're looking at today is a dusty, unassuming document that quietly held the blueprint for the entire AI revolution. And for a really long time, it was a secret the world almost entirely missed. Just look at the names on this 1986 letter to the journal Nature. You've got David E. Rumelhart, Jeffrey E. Hinton, and Ronald J. Williams. It's titled, Learning Representations by Back-propagating Errors. Now today, Jeffrey Hinton is known as one of the godfathers of AI. But back when this was published, these ideas were incredibly radical. They were proposing a completely new learning procedure for networks of neuron-like units. It was a true slow-burn secret. 1986. Just think about that for a second. We were still listening to cassette tapes. Yet the mathematical foundation for how neural networks learn was already sitting quietly on a shelf, just waiting for the rest of the world to catch up. Okay, so let's unpack this secret from 1986 and look at this quiet revolution in AI. So what was the actual breakthrough these three researchers managed to put down on paper? Well, the authors wrote, quote, internal hidden units, which are not part of the input or output, come to represent important features of the task domain. End quote. What is absolutely crucial here is that word hidden. See, before this paper, simpler neural networks, called perceptrons, couldn't really have true hidden layers because we just couldn't figure out how to train them. They couldn't learn complex internal representations. But this paper, it proved that a general-purpose procedure was powerful enough to let the network actually decide what it needed to represent to solve a problem. It was a literal game changer. So how does this actually work? Let's talk about bad-tasting soup and how neural networks learn. I promise we can break this down perfectly without touching any calculus. Imagine the neural network is a head chef, and they're trying to create the perfect soup. The paper introduces this concept called total error, or E. In our kitchen analogy, this total error is simply the bad taste of the soup. It's the exact measurement of the difference between the actual output, the soup we just cooked, and the desired output, the delicious soup we actually wanted to make. The chef's entire goal? Reduce that bad taste to zero. To pull this off, the network uses two distinct passes. First up, the forward pass. This is simply cooking the soup and then tasting it to see how it turned out. The ingredients move forward through the kitchen, straight to the bowl. But then comes the real magic of this paper, the backward pass. See, because the soup tastes bad, you can't just yell at the kitchen staff to make it better. You have to trace that bad taste backward through the kitchen to figure out exactly which specific ingredients to adjust. So the whole mechanism is this crucial four-step process. Step 1, taste the soup. Step 2, measure the bad taste. That's calculating the total error. Step 3, trace it back to the ingredients. The paper calls this propagating the derivatives backwards. And step 4, adjust the recipe. In the paper, this means adjusting the weights of the connections to minimize the error, a process known as gradient descent. It's basically just methodically fixing the recipe, one tiny tweak at a time.
Now let's unlock those hidden layers and meet our intermediate taste testers.
Let's take a look at who is actually doing the cooking and tasting in the middle of our hierarchy. This is where those magical hidden units come back into play. In this diagram, straight from the 1986 paper, you see an input layer at the bottom and an output layer at the top. But sandwiched in between are these nodes labeled hidden units. Before backpropagation, networks could really only connect inputs directly to outputs. It was a very flat kitchen, so to speak. Backpropagation is what finally allowed for these complex, bustling middle layers. You can think of these hidden units as intermediate taste testers. They don't know the final recipe, and they certainly don't buy the initial ingredients. The paper explains that the learning procedure must figure out under what circumstances these hidden units should be active to help achieve the desired final soup. They autonomously figure out exactly what features they need to care about, which is something older methods just couldn't do. And this brilliantly illustrates that exact concept. The authors trained a 5-layer network to learn family tree relationships. Notice the white squares? Those show the activity levels of the units. They proved that the hidden layers successfully learned to encode really abstract concepts, like specific people and their relationships, such as has-aunt, into distributed patterns of activity. Think about that. The intermediate taste testers figured out how to categorize family trees without explicitly being told the rules of human genealogy. It's incredible. Next up, let's look at the math. Here is the chain rule, simplified, and how we go about tracing the blame. Okay, so how exactly do they calculate how much to change each ingredient? The paper uses the chain rule, which involves partial derivatives. But let's keep it in the kitchen and translate that into plain English. Imagine the customer at the output layer says, "The soup is way too salty." We don't just randomly change everything. We ask the sous chef in the penultimate layer. The sous chef says, "Hey, I just combined what the prep cooks gave me." So we go down to the lower layer, the prep cooks, and find the exact one who added the salt. We then adjust the instructions specifically for that prep cook. By asking down the hierarchy layer by layer from top to bottom, we mathematically trace the blame back to the exact source. And that brings us to the massive aha moment of the paper. Rumelhart, Hinton, and Williams wrote, "This means that we know how a change in the total input X to an output unit will affect the error. Because they can compute this step-by-step backward chain, they know exactly how tweaking any single state or weight in the entire network is going to fix that bad taste in the final soup." But we need to talk about why it sat quietly for so long. Let's look at the flaws in the design. So if this blueprint was so incredibly brilliant, why didn't AI immediately take over in 1986? Well, it had some serious practical flaws. And to be fair, the authors were brutally honest about this. They admitted in the letter, this method does not converge as rapidly as methods which make use of the second derivatives. In plain English, it was painstakingly slow. To learn even a simple task, the network required thousands of sweeps through all the data, making tiny, tiny adjustments each time. In 1986, computers simply did not have the juice to make this practical for massive real-world problems. Furthermore, they identified a mathematical trap called local minima. Going back to our kitchen, imagine the chef is tweaking a recipe to make it better and better. Eventually, they hit a point where any small change makes the soup taste slightly worse. So they stop, thinking, I have the perfect recipe. But they're trapped in a local minima. It's really just an okay recipe. They completely miss the fact that if they drastically changed the base entirely, they could find the global minimum, the truly perfect ultimate recipe. Backpropagation really struggled with getting stuck in these merely okay solutions. And finally, there was the biology problem. The scientific community at the time was heavily focused on neuroscience, but the authors themselves conceded at the end of the letter, the learning procedure in its current form is not a plausible model of learning in brains. Because human brains don't appear to propagate error signals backward through synapses like a math equation, many scientists just dismissed it as a neat trick rather than a true path to intelligence. And that's exactly why the broader research community looked the other way for decades. Which brings us to our final section, the next unsolved breakthrough, and waiting for the future. So the paper proved multi-layer networks could learn, and then it mostly went to sleep in a drawer. To summarize what you should take away from this explainer, the 1986 blueprint was an absolute mathematical breakthrough, but it was limited by the reality of its era. It required immense computing power for those multiple network sweeps. It risked getting trapped in local minima, in lower dimensional subspaces, and it was deeply biologically implausible. Those were the exact hurdles that forced the genius of backpropagation into hibernation. Which leaves us with a pretty fascinating final thought. We know backpropagation eventually won, right? It's the engine of modern AI. But if it was too slow and computationally demanding for the machines of 1986, what massive technological shift, decades later, finally gave this dusty blueprint the raw power it needed to conquer the world? What was the missing puzzle piece? That's a question that completely changes how we look at the hardware sitting on our desks today. Thanks for exploring this 1986 secret with me. Keep learning, and I'll catch you on the next explainer.